at this point, what we tend to do is pivot a little bit and look at a couple other concepts that are directly related to ways of thinking about this kind of data, this kind of procedure. So let's talk about sampling. I'm gonna just open up a little drawing pad here. And let's think about sampling. So, I said this before, and I'll just go, just kind of repeat it a little bit. When we have a population, we know everything, right? We know everything, every measurement of something or every count, whatever that might be. And when we sample, we're taking some subset of this population, and we want to sample in such a way that what we end up with is representative, right? And so what we might get out of this is an X bar, right, that approaches our value of mu. And if we're thinking about our, this is mean, of course, this is our mean. If we're thinking about it in terms of mean, we want to approach the population mean. That's going to be our best sense. If we can, the better we can do that, the better position we're in, right? And when we say this, we want our sampling to be representative. We want the culmination of these samples to effectively approximate the population, right? So there are some words, I didn't use these words before, but I just want to point out that when we talk about X bar, what we're talking about is a statistic of the data. In this case, or in this sense, a statistic is formed from an analysis of a subset of the data. When we talk about mu, we're talking about a parameter of the data. And that parameter is a sort of fixed, it's a fixed value, right? We have some static data, the parameter is going to be fixed. It's not going to vary. However, with a statistic, if we sample once and then we sample again, this statistic is going to change. And if we're thinking about X bar, well, let's say we sample over and over again, we might have an X bar, X bar 1 and X bar 2, X bar 3, and so on, right? Up to X bar n. And it might occur to you, okay, well, in this sampling process, if we want to better approximate the population parameter, or if we want to decide for some other reason that this is the population parameter, we might take the mean of all of these. And so we've got a distribution of values that we use to get X bar, X bar sub 1. And then we have a distribution of means that we can use to approximate, to the best of our ability, the population parameter mu. This is something that we can do fairly simply with Python. It's something that, well, let's think about this. Yeah, let's write some code for this. It's not too tricky. And I'll just make that a little bit bigger. And this is kind of a soft introduction to something we'll dive into quite a bit later in terms of sampling, a little bit deeper. So one of the things I'm going to do, I'm going to import the choice function from the random library. So from random import choice. Now, what does choice do? Choice is a really helpful function. Let's say we want to choose something randomly from 1, 2, and 3. If we run this, what we're going to see is either a 1 or a 2 or a 3. And let's see, I actually need to navigate to just make sure. Okay. So we get a 1, and then we get a 2, and then we get a 1, and a 1, and a 1. Do this all day, right? So this is going to help us in, sampling from, or trying to approximate a population parameter, right? So from random import choice, and then I'm going to get some samples. I'm going to get a range from which we're going to sample. So this is going to be the range from 0 to 100. I'm going to do 99 plus 1 because then we're sort of explicitly stating that we are including 99 in this. And let's take some samples. I'm going to collect my samples into this list called samples. And let's make another variable here. Let's call this number of samples. And let's set that to 5. So we're going to sample 5 numbers from the range 0 to 99. And I'm going to say for whatever, when I do an underscore like this, that's how I read that, for whatever, because we don't care about it, for whatever in range 5, or sorry, num samples, right? And we're going to just append a choice from our sample range. And now we can print the mean of the sample range, all right? And we can print the mean of our samples. So this is an illustration of kind of, population versus sample. So this is going to be, I'll call this mu, and I'll call this x bar. Okay. So mu is 49.5, x bar is 46.4. Mu is 49.5, x bar is 32.2. Mu is 49.5. Notice our mu never changes, right? It is not going to change. X bar obviously is varying quite a bit. 45.4, 51.6, 49, 49.4, 32.6, 63.8, right? It's going above and below what our population parameter is. And you might wonder, well, how does it spread above and below our population parameter mu? And a way that we can do that is we can, simply we can wrap this into a function. Let's say, I'll just make this a function. Def get samps, and let's pass in number of samples. We'll set that to 5 by default. And what else should we do? Maybe we can do from the sample range, we'll do a low to a high, and we'll set low by default to 0 and high by default to 99. And is that it? And then we just want to return our samples. Okay, so we're going to is that how we should do that? Maybe we should get this sample range outside of this. Yeah, let's do that instead. So we'll define a sample range out here, and we'll keep that at 0 to 99. And up here, what we'll do is just do, we'll pass in a sample range so that when we call that, it'll work like that. Okay, so that looks like it should work. I just need to fix this. So we can get the mean of the sample range, and then we want to get the mean from get samps, which we can do like so. So here we're getting num samples of 5, and we can do this repeatedly. Now, since we can do this repeatedly, maybe I can take a different approach. I can get the mean of the means, okay? So let's do this. Call this means, and we'll just make that an empty list. I'm going to do just a simple collector here, and let's get 100 of these. So for whatever in range, we'll get 100. We'll say means.append, and we'll append our number of samples. Actually, I think I set number of samples. Let's do this a slightly different. Let's say num samples gets 5. And I'll just pass in number of samples instead. So means.append. So we're collecting 100 means from this sampling process. We're going to see the population parameter here because of the print on line 96. And then we can see, well, let's do this. Let's copy this line. And so let's say call this mean of means. And we're going to get the mean of means. Right, there we go. The mean of means. So hopefully that'll work. There might be an error in there somewhere, but let's find out. Okay, so notice our mu is 49.5. Our mean of means is 48.302. And if I keep running this, what we're going to see is we are close to the population parameter. And if we want to get closer to the population parameter, and this is going to be a theme, well, we can take more samples, right? So if we take 1,000 samples, we have tightened this up a little bit. Now let's take 100,000 samples and see what we get. 49.49. That's really close to 49.5, right? 49.56, 49.539, and so on. So this is just to sort of drive home this point and inform our idea of the concept of spread. You know, maybe a takeaway here, a small takeaway, is the more samples you have, you tend to do better. you tend to do better in all things. If you have more data, your machine learning algorithms tend to do better. If you take more samples, you tend to have a much better idea of the distribution of things that you're working with, right? You tend to better approximate your population parameters. So your X bar gets closer to mu, likely does. So I'll paste in this code. This goes a little bit further than what's on the slides, but I think it could be helpful to look at this and play around with it. In fact, I'm going to update it on the slide as well, just to have it there for y'all if you want to look at it there. All right. Okay, so this is going to, you know, that may seem like an aside, but let's go into the actual aside that I'm planning to have right now before we get to our measures of spread. Most of today is going to be in regards to our measures of spread. So let's touch on this concept of continuous versus discrete. And I think it's important to talk about this early, and it's going to keep coming back around. So let's just kind of get into it. So we have two concepts in terms of numeric data that we're going to think about these as two different concepts. I almost said two discrete concepts, but that's likely to be confusing if I say it that way. So we have what we call continuous data, and we have what we call discrete data. And if we're thinking about it, you know, there are other ways we can think about data, other ways we can categorize data, but these are the two big ones for what we want to think about right now. So let's talk about continuous data first. Let's imagine we have a concept like time. And here's time's arrow. and maybe we're going from some specific moment, which we'll call 0, and we're going to go up to 1. So say 1 second or 1 minute, 1 hour, whatever, however we want to think about this time. And of course, this can go infinitely into the future. Now, what happens if we look at 0.1 to, well, let's do 0.1 to 0.2. If we bring this out and we say this is 0.1 to 0.2, we still have we have an infinite number of measurements within this space, right? So we could say, well, now let's look at 0.11 to 0.12, right? We can do this infinitely if we have a precise enough instrument. So when we think about something being continuous, we have the potential for infinite precision, right? We have the potential for infinite precision that is contingent on our instrument of measurement. Practically, however, at some point we have to discretize this because we don't have any tools that have infinite precision. Just when you get down to it, we don't have that. That's fine, but we want to think about continuous as being in this idea of if you keep looking in, right? If you keep looking in, you can get 0.112119111 with an infinite number of decimal places. So that's how we're going to think about continuous. And because of this sort of property, that is going to distinguish continuous distributions when we get to them from discrete distributions. For now, we want to mostly think about continuous in terms of infinite precision, which lends itself to a word that I want you to associate with this, measurement, right? Measurement. When you're measuring something, if you have a precise enough instrument, you have infinite precision on that measurement. You know, infinite number of decimal places. So we're going to distinguish this from discrete very simply and just say discrete is to be associated with the idea of counting. And to make this kind of still sit on a number line, let's say we have 0 to 10 now. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. It's not bad. So between 0 and 1, well, there's nothing. It's nonsensical in a discrete concept to think of something as being between 0 and 1. If you're counting how many people are in a room, you don't think that there's 7.3 people. You think there's 7 people or there's 8 people, right? If there's 7.3 people, you have some issues that you have to deal with. And so let's, the way that I like to visualize this is that these are all boxes, right? This is the 0th box, the first box, second box, third box, and so on. There is nothing in between these boxes. They're right up against each other. And so we are not going to subdivide these. That said, we can have a situation where, let's say we're talking about classrooms in a school, and we ask the question, well, what is the average number of students across, 20 classrooms? In that case, you can have an X bar, right? You can have an X bar that has, says like, I don't know, 21.3 students. Because X bar is, or, maybe it's X bar, maybe it's mu. It depends on if we're sampling or if we're taking a population parameter. But we can have a fractional value because this value, in essence, doesn't exist in that world. We're not going to have a classroom with 21.3 students. We're going to have a classroom with 19 students or 17 or 25 or whatever. So that's kind of just an introduction to thinking about data in terms of being discrete or being continuous. This is going to come back around. I think I go over this. I think I go over it 3 times because we're going to talk about discrete distributions. We're going to talk about continuous distributions, and this is going to be important in both those contexts as well. Okay, so let me just. So now we're going to talk measures of spread, and we kind of split these 2 lectures, right? Centrality versus measures of spread, but they're very, very closely tied in. Our measures of spread are usually in relation to something central, okay? So there are a few concepts here that we're going to cover: 5-number summary, IQR, determining outliers, which we're going to do in relation to the IQR, variance, and standard deviation. I just want to be really clear about this. These are sort of old school, and these are what you're commonly going to think of when you think about measures of spread. There are other measures of spread that we don't cover here, but you know, that's something that if you want materials on, I can definitely point you at something. Okay, so the first one we're going to talk about is the 5-number summary. So 5-number summary is, how do I say this? It gives you a quick snapshot of some data. And I think it's nice to approach things in terms of the 5-number summary because you can just immediately describe what's going on. This is helpful for, like, say, baseball statistics. It's used all the time. For those home sale, ideas, or sorry, that home sale problem that we kept encountering. This is a good way to think about that. What is the cheapest house? What is the most expensive house? What was the median house value? We often think about sales of items in terms of median, right? And all of this is related to the median. And notice that Q1 is the 25th percentile. It turns out Q1 is the median between the minimum and the median. Q3 is the median between the median and the maximum. So what do we need to write a 5-number summary function? Let's think about that. We need the minimum, but you know, that's easy. That's really easy if you have some data. That's a built-in function, min. The maximum, well, that's easy too. That's a built-in function called max. Median, well, we wrote median last time. And so we'll need that again this time. I can snag that from above if anyone needs it. And then what do we need to solve Q1? So this is interesting. We need to find the median between min and the median. So that might be challenging a little bit. I'm gonna throw this problem at you. It's you can at least get the minimum, the median, and the maximum, of course, but it might be a little more challenging. Not too challenging, but you might stumble a little bit when you try to get Q1 and Q3. That's okay. We're gonna code this out. I think walking through it, talking through it is going to make it clear what's going on here. So let me grab code for all of you, and I'll leave this up here somewhere. Leave it right there. And you'll need the mean function and the median function. You don't need the mean function quite yet, but you'll need it soon. Okay. So here's mean and median. So I'm just deleting out the extraneous stuff from that. Okay. All right. So let me give you the challenge. Code the 5-number summary. And try to make this a little bit bigger. Whenever I draw on these slides, Notice it sort of doubles or undoubles. It's kind of a, try to make it readable. Okay. All right, so I'm gonna set 5 minutes for this, and yeah, I'm gonna set 5 minutes, and I'll ask when we get down to the 1 minute mark if you want 2 more minutes, and do your best on it. I'll ask, and if we're not gonna add 2 minutes, then I'll just have you post what you've got so far. If we do add 2 minutes, then we'll have you post right before our time runs out. Okay, so I'll set this for 5, and go for it. Do your best. All right, give me a thumbs up in the Slack if you would like 2 more minutes on this. Okay, I'm gonna go ahead and add 2 minutes. I'm gonna set it to 3 minutes because of, to make up for the minute that I just cut off. Okay, we're in the last minute. If just make sure you post your code, whatever you've got so far, into the Slack. When our minute rhymes. Well, now, if you could. So go ahead and post whatever you've got. All right, and I'm going to go ahead and code through this. This is not the easiest function to write, and definitely don't feel discouraged if you didn't get to a solution on this. This is one of those functions that, well, it's going to take up a lot of space the way I write it. So I'll just say that. But there are ways that we could be a little more compact if we wanted to, or if we needed to. Okay, so this is going to be 5 number summary. And we're going to pass in a list, right? It could be a list of any numbers. We're not going to expect that list to be in order. It's going to be in whatever order we find it. Now, like I said, we can get 3 things off this 5 number summary immediately. We can get the minimum, the median, and the maximum. And that's easy enough to do. So I'm going to say min, that's just going to be the min of the list. Max, that's just going to be the max of the list. And we've got the median, which is going to be the median of the list. Okay, so that's a nice start. Remember what we need to do for Q1 is we need to find the median starting at the min value going up to the median. So how do we do that? Well, that implies that this needs to be in order. So I'm going to first sort the list. I'm going to do sorted list, and we'll just grab that. Okay, so now that we have that, we come up against a question, are we going to include the median or not? And there are differing opinions on this. There's a 5-number summary where you exclude the median, and there's a 5-number summary where you include the median. And the only way that we really have to worry about that is if it's an odd length list, right? Because if it's even, well, we don't include the median anyway. The median is sort of just left out because the median is the mean between the two central values. So then the question is, for an odd length list, do we include the median or don't we? There's differing opinions on this. I'm going to include the median because it tends to be more common. I was taught to not include the median, but I kind of revised this recently, and most 5-number summaries will definitely include the median. So if the length of our list, our original list, right, if that is odd, so if mod 2 is equal to 1, then we know that that's odd. So we can, at this point, separate our data, our sorted data, into a lower half and an upper half. So let's do that. So our lower half is going to be that sorted list. And we're going to start at 0. We want to include the smallest value. And we want to go up to the length of the list divided by 2 plus 1. Okay? So I'm going to first cast this to an integer, and then I'm going to add 1 to it. So remember, you have to, if you divide, that makes it into, well, it makes it into a float. We could also, if we wanted to, this is not a problem. We could do floor division. That's going to be the equivalent, right? For the sake of where we're at right now, I'm going to go ahead and leave this at as casting because I think maybe some people aren't as comfortable with floor division, and that's okay. So let's print this lower half. And if this is our lower half, it shouldn't be too hard to figure out the upper half. Okay. So let's do this. Let's say upper half. So I'm going to get that out of there and get that out of there. So upper half is going to be from this initial value, okay, up until the end. Oh, wait a minute. Is that right? I think we want to do that. Okay. All right. So let's test this with an odd length list. I'll make A, and we'll do A is, I don't know, let's do 1, 9, 12, 78, 45, 53, 1, 2, 3, 4, 5, 6, 2, 22, 7, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, good. Okay. And we'll just do this to verify that we're on the right track. And we're just going to look at the upper and lower halves. So let's print the upper half as well. And we also, to make this a little easier, let's print the sorted version of A so that we can see it in the context of what we're writing. Okay, so 1, 9, 12, 22, 23, good. 23, 24, 25, 24, 45, 53, 78. Okay, so what we need out of this function is, our Q1 and our Q3. This will satisfy for an odd length list, but we also have to accommodate for an even length list. I'll go ahead and get rid of these print statements. And let's write what we need for an even length list. And that'll be, again, we need this lower half and an upper half. In this case, however, we don't need the +1. And there's actually an easier way that we could do this where we don't need this condition, and I'll show that in just a second. So Q1 is going to be the median of the lower half. Q2 is going to be the median of the upper half. Maybe I'll just test this really quick, just make sure that this is doing what we expect. Okay, so I'll call this again with a different data set. I'll just take the same one and I'll add another number, 55, and we will get the 5-number summary. Well, we'll look at the upper and lower halves of B, and we also need to print the sorted version of B. Oh, B is not defined because it's called A. All right, so here's the whole thing: 1, 9, 12, 22, 23, 24, 45, 53, 55, 78. Okay, that is working as we expected. And let's go ahead and finish solving this. All right, cool thing about this is at this point where we basically solved it, we've got the min, Q1, the median, Q3, and the max. And we can just return all of those: min, Q1, median, Q3, and max. And we're just returning all of those. This is going to return them as a tuple. Oops, that says Q2, it should be Q3. And we can now look at the 5-number summaries for both A and B. Oh. Okay. All right, so I'll just snag this. Huh. Oh, I see what's happening. Okay, one sec. I'm still printing stuff up here. Okay, and then sorted of A, number summary of A, sorted of B, number summary of B. Let's try that. Didn't save it. We save it. Run that again. Oh, something weird is happening with my terminal. Let's see, yeah. All right. There we go. All right, let's try that again. Okay, perfect. So notice here we've got the data, we've got our summaries. Like I said, this is not, don't be discouraged if you weren't able to write this function during that time. It's not the easiest function to conceptualize on the fly. But notice that this is working as we expected, and it also gives us a sense of what this data is, right? We've got our min, we've got our max, these are represented here, we have our middle value, we have the middle of the middle values. And so this is really nice. We can talk about a data set, we can get a sense of a data set very quickly with a 5-number summary. So I'll go ahead and paste all of that in. And then we'll work on some stuff that is not quite so complex. Oh, I was going to mention this. We can tighten this code up a little bit, but let me give you this code first, because I just want to show you this little bit of a sort of small code optimization. So here we've got basically the same code. There's only one tiny difference here. So what we can do, and this may seem like evil magic or something, but I'm going to replace this 1 with a condition. And let's do that. So this condition in here will either evaluate to true or false. And if you think about false, false is like 0. So if it's an even length list, we're going to add 0. If it's an odd length list, we're going to add true or 1. So it's just a small optimization. We run this, we should get the same results. Let me just run that. Run that here. And we do. We get the same exact thing. So it's a slight code simplification. It's a little bit cleaner, a little bit nicer. We could compact this a little bit more. For example, if you think about it, we don't need this min. We can move this down to here. And I'll share this optimized version in just a second. We don't need this max because we can just calculate that down here. And we don't need this median because, again, we can just calculate that at the bottom. So this is just a little bit tighter in terms of the code. We could tighten this up a little bit more, right? We could replace Q1 with median of lower half, Q3 with median of upper half. We could, in fact, turn this into, if we were trying to be sadistic, we could turn this into a one-line function, which I'm not going to do. But feel free to try to do that by sort of compactifying your code. It is possible to turn this into one line. Not saying that's a good thing to do, but it's something that you can definitely do. So I'll share this slightly more compact version, and feel free to play around with that and make it compact, brutally compact. I don't know. If you play around with Code Wars, you're going to see this a lot, where somebody gives a solution to a function, and you see it, and you're like, "Wow, that's really cool. I have no idea what it's doing," and it's one line. And as impressive as that is, it's very important for your code to be readable. I know Clark talks about that a lot, but I just want to reiterate that. There are times where I'll make the code a little bit tighter, but in general, I'm going to try to write code that's going to be readable. And at times, it is good to really make code compact and tight. It depends on who you're working with. Okay, so now that we have the 5-number summary, we can test this on some data. It's easy enough to do. But I want to talk about a concept within the 5-number summary that is really important and that we use. We use sometimes to define what is and is not an outlier for data. We might choose to do that at times. So there's this idea of the interquartile range. And this is a very simple concept, very simple function to write. It's just Q3 minus Q1. So it's the median of the upper half minus the median of the lower half. And that's the middle 50% of our data. So that's very helpful. If you want to think of the data that is representative of the data set, we often will think about the middle 50%. So this can be a very, I think a quick function to write. And that's the next breakout. And I've got a little bit of a little code to paste in. So we're going to define A and B. We're going to define A and B. Those are just ranges of numbers. And you're going to show the 5-number summary and IQR of A and B. Notice that you have to code the IQR function as well. So think about how you would do that. And the hint here is you're going to depend on the 5-number summary function to which you're going to call within the IQR function in order to calculate this. And remember, IQR is just Q3 minus Q1. So let's do 4 minutes on that. And yeah, go for it. All right, so post what you have for the IQR, and oh, sorry, I didn't see this question. Interquartile range, 50% median of upper half, 50% median of lower half. Yeah, so the Q3 is the median of the upper half. Q1 is the median of the lower half. So that hopefully that clarifies what's going on there. And so what we get from the IQR represents the middle 50% of the data. And we can see that pretty clearly. Let's just code. I'll just code through it really quick, and we'll go from there. So let me snag these. So we've got A and B, and we're gonna look at the IQR of A. So IQR of A and the IQR of B, and we'll write this now. So def IQR, we're going to pass in a list. So the first thing you're going to do here is, well, really the only thing you're going to do here is you're going to call out to the 5-number summary, and you're going to get 5 things out of this. So here's 5-number summary. I'm going to call to that, and I'm going to get out of it the min, Q1, the median, Q3, and the max. And I'm just copying this as a placeholder. I'm going to replace max with an underscore because we don't need it. We do need Q3. We don't need the median. And we don't need the min. And at the end of this, we're just going to say return Q3 minus Q1. So we've got that. That should work. So let's find out. So in this, let's actually print this out. Let's print let's print A and print B, and just notice what we're getting. Okay, so there's a range of 25 of the IQR. So if we want to see this, let's print the 5-number summary of A and B. That'll illustrate it just a little bit further. And if we look at the median of, sorry, not the median, but if we look at the, let's make this a little bit bigger, easier to see. We look at Q3, which is somewhere over here, right, 37.5, right? We look at Q3 being right up here, and we look at Q2 being right down here. So 1, 2, 3, 4, 5 values sit in there, and you know, there's 6 values sitting out here, but we think of this as being the middle for 50% of the data. All right, and this is why we have, well, just to be clear, we are including those, that 12.5 and 37.5. So it's not 35 minus 15, but it is 37.5 minus 12.5. So we assume that values in this range, if we were to sample, 50% of the values should fall within that range. Is a way to think about the IQR. That's not entirely accurate, but it is a very helpful, it's a very helpful kind of statistic when we're looking at certain kind of phenomena, like, you know, especially things like baseball averages, sports averages in general. And although we don't cover it here, box plots are visual representations of the IQR. So if you've worked through that material on Learn, you are essentially looking at a very quick representation of data of the IQR of the 5-number summary. Okay, so what's a reason why we might consider the IQR? Well, it gives us a sense of spread, right? It gives us a sense of how far around the median we stretch in one direction or another. Like we go we go half the IQR above the median, half the IQR below the median, reasonably, right? So that's one really nice thing about it. It's a measure of spread. The other thing that it might help us do is determine outliers. So there's a way that we can use the IQR. And this is a little bit arbitrary, just to be clear. It's a little arbitrary. If we know the IQR, black. If we know the IQR, we can multiply this by some value, which I'll call an outlier coefficient. But in general, we'll think of this as 1.5. So 1.5 times the IQR above Q3, right? That's a high outlier. Or below Q1. So Q1 minus the IQR would be a low outlier. So this is arbitrary, all right? This number, 1.5, we could choose a different number depending on the data that we're dealing with. We always have to ask the question, do we actually want to remove outliers? There are a lot of cases where we don't. But this is a classic way of determining outliers. If you've got some data and you know the IQR, if you look within that data and see that some of the values are 1.5 times the IQR greater than your value at Q3, you might say, okay, well, that's an outlier. Let's not include that in our data. So I'm going to have you code a detect outliers function. And this might be a little bit of an intuitive leap. Again, do your best on it. We're going to code through it. And then we'll take a break immediately after that. So there are a couple things that you're going to need here. I have a little starter code for you that is what we're seeing there. So def detect outliers, you're going to pass in a list. And then we've got this outlier coefficient. By default, it's 1.5, but maybe you want to make it 2 or 3.3 or something like that. So I'm going to set 4 minutes here. Notice that, well, just read through this. Everything you need should be here. You're going to need to utilize the prior functions. Oh, did I not paste in? I am sorry. Let me paste in my IQR function because you will need that. Okay, sorry about that delay. And I will set a timer for 4 minutes. Here, let me just stop us for a second and make sure that we're all on the same page about the math here. So if we're thinking about the IQR, an outlier is going to be the IQR, 1.5 times the IQR, right? So 1.5 times the IQR above Q3, or it's going to be less than 1.5 times the IQR below Q1. So let's say we have some data and we've got Q1, Q3, and here's our min and max. If we have a data point here, if this data point is greater than 1.5 times the IQR above Q3, then we're going to consider it an outlier, right? And here, if we have a data point that is, less than Q1 minus 1.5 times the IQR, then that would be an outlier. So let me just put this up in the corner. And then I think we were somewhere right around 3 minutes, so I'll put 3 minutes back on. Let's see how we can get this to fit. All right, so let's go ahead and work through this. And I realize some of these are pretty challenging at this stage. I think any of these functions that we're working on today, it's good to come back through and look at the code, try to pick it apart, watch the video for a bit of a refresher on it. And I promise these things will click pretty well pretty soon. So let's go ahead and code through this. Let's see, let me grab that starter code. So we've got detect outliers. We're assuming a list is going to be passed in, and I can just make a list really quick. So just define this as A, and let's do 12 and 32 and 54 and 45 and 7 and 89 and 601. Okay, and let's do 12,549. So there's an obvious outlier in here. We're going to hopefully detect that. So we've got this coefficient set at 1.5. That's what we're going to use by default. I'm going to return a list containing all detectable outliers, right? So again, we can call out to 5-number summary. And we're going to pass in that list. We're going to get a few things out of this, namely Q1 and Q3. That's all we really need to get out of that. And we can get the IQR as well by just calling the IQR function on that list. Okay, so at this point, what we're looking at is sort of a common accumulator pattern using a list. I call those collectors. So we're going to collect the outliers into this list called outliers. And we can look at each number in this list. Maybe I'll just make this a little bit bigger. So for num in list, we can check to see if it's less than Q1 minus the outlier coefficient, which could be 1.5 or something else, multiplied by the IQR. And if that's the case, then we're going to grab outliers, right? Outliers that append num, and that will collect our low outliers. What about our high outliers? So this is one of those instances where we're not going to use an if-elif. We're going to use an if and then another if. And we can say if num is greater than Q3 plus the outlier coefficient, then we append the number. So that should work. Let's see. We'll return outliers and we'll print this. So detect outliers on A. And why don't we put a negative something in here? So negative 1,000. Close that. Too many values to unpack. 1, 2, 3, 4. Oh, I'm missing the max. All right. Okay. Just missing one value there. And we've collected negative 1,000 and positive 12,549. There are other ways that we can think about this, right? Like, well, what would our outlier coefficient need to be in order to retain those two values? We could play around with that. Would it be 20? I don't know. We could even write a function that would, define what this outlier coefficient would be, or what multiplier it would return, what multiplier we would need in order to retain all values in the list, right? There are different ways that we can approach this, depending on what our needs are. I think in general, when we're looking at most data or a lot of data, 1.5 is going to be a decent coefficient for detecting outliers. Okay. I know we're taking this break a little bit late. Let's take 5 minutes right now. And when we come back, we'll get into, we'll just continue forward. If we don't finish out measures of spread today, we'll carry that into the next lecture, and that's fine. Okay, so I'll just set a 5-minute timer, and I'll see you all back here in a little bit. Okay, I think we've got one more thing that we'll think about in regards to outliers. Let me just scroll through. Yeah, so I think this will be interesting. I think I do still need to share this code snippet, don't I? Apologies. I'll just do that now. Okay. So now that we can detect outliers, can we remove outliers from some data? Right? The natural progression here. So let's think about this. Let me just find the snippet for remove outliers. Here we go. So we're going to write a function called remove outliers. And it'll take a list as input and return a new list with all values that are not outliers. Now, there are some things that you might think about here. What are your parameters for remove outliers? Right. This is going to be dependent on the prior function. So your parameters, like you're probably going to need to define an outlier coefficient, and so you're going to pass in some list of values. And why don't I give you some values to work with? These are those house prices that we looked at a couple days ago. A couple days ago. So there's some data to test. It turns out there are 2 outliers in there, or maybe 3. I know there's at least 2. Right, that 1285 is likely to be an outlier. So go ahead. We're going to take, how much time do we have? Let's take 5 minutes on this actually, and yeah, see if you can get that to work. It is going to be dependent on the prior function. All right, so let's go through this. This is a bit of kind of an expansion of this detect outliers function. And as such, well, we're going to use the detect outliers function for sure. Let's see, did I paste in? Yep, there we go. So we're going to use A, and this function is called remove outliers, which we'll call on A. So there are a couple things we'll need here, right? We'll need both the list and the outlier coefficient. So I'm just going to grab those from our detect outliers function, and we're going to go from there. So we need to get the outliers in order to know that we should remove them. And so with that, we'll say, we'll just get outliers like this, and we'll call out to detect outliers, and we'll pass in the list and the outlier coefficient. So we've got that. We're going to have some output, right? You know, this is, we can take a couple different approaches to this. Output here is just our modified list, right? So one way that we can do this, we can say for num in list, for each number in our input list, we can ask if the number is not in the outliers, then we can append it. So we are essentially using this as a sieve to take values from one list and put them into another list. So output.append will append the number, and we can return the output. So let's see if that worked. And just that out there. Okay, so here's our list with something removed. So 590, 615, 575, 608. What are we missing here? It looks like we're missing 350, right? It looks like we're missing 408, and we're missing 1285. So we're missing these three right here in the middle. Let me show you another way to write this. So I'll put this in the Slack first. We could, instead of taking this kind of additive approach where we create a list and put things into it, we could instead say output is going to get a copy of our list. So list.copy. And then for each number in our outliers, if the number is in our output, then we say output.remove that number. So that should get us the same results. And it does. Which one of these is better? Well, I think arguably this version is better because it's reductive. And notice that we're only going to loop as many times as we have outliers. We're not going to loop across the entire input list. So this will have less iterations as a result. Does it matter which one of these you do? No, not for this kind of problem. Maybe if we were to scale this to some much larger application scenario, something like that, maybe it would matter. It doesn't matter here. So let's continue into variance and standard deviation. And I think we'll see. We'll see if we have the time to cover all of this today. We might stretch this over into the next class. Okay, so variance. Is one of our measures of spread. And I'm going to say this sort of, verbally. How verbally do we think about, or how do we think about this verbally? This is the average squared distance between each data point and the mean. So that's easy enough to say. What does that look like? What does that look like mathematically? Well, how do we take the average of something? Well, we add everything up and we divide it by the number of items. So we're going to add a bunch of stuff up and we're going to divide it by the number of items. So n here is the number of items, and we're going to look at all items from the first item to the nth item. So that covers the average part of this, right? What about the each data point and the mean part of this? Well, let's imagine we've got a data set called X, and X has the values 1, 2, 3, 4, and 5. This value at 1 is X sub 1, the way we're going to think about this. So if we were to get the average of this, right, what is that? That's 9, 12, 14, 15, divided by 5. So our average is 3. Maybe that should have been obvious. But, you know, so let's say this is our X bar or our mu. We don't know yet if we're talking about a population or a sample. It does make a difference in this case. If we want to consider the squared distance between each data point and the mean for every one of these, then we're going to say, well, 1 minus 3 squared, right, is one of our values, is one of our distances. So that would be x1 minus mu squared. And then we've got x2, which is 2, right? So x2, which is 2. x2 minus 3, quantity squared. Think about what the squaring does here. It's going to get rid of the negative values, right? 1 minus 3 is negative 2. Negative 2 squared is 4. So we get, this is going to be only a positive value in this case. So if we want to be, you know, kind of representative of this mathematically, this is going to be x sub I minus mu squared. And all of this is going to be, we represent this as sigma squared. All right, so sigma squared, this is for a population. And let me just rewrite this. So we've got a population version of this formula. We have a sample version of this formula. There's a reason for this, which I will probably spend the rest of class explaining. But we'll look into it. I don't want to get too deep into it, but I think it's really interesting, and it's definitely something to read up on at some point, because it's a little weirder than you might think in terms of variance. Okay, so the average of the squared distances between each data point in this list of data X and the mean, right? So that's our distance for a population, and this is going to be the first item up until the last item. And here we've got basically the same formula, but we represent it differently. When we represent populations, we usually use Greek characters, right? That's Greek. And when we represent samples, we usually use, when we're talking about the moments or the measurement statistics, however we want to think about it, of a sample, we tend to use a Latin letter, and here we use s squared, right? So s squared is our variance. And this is going to be essentially the same formula, but we are going to say, we are not going to take the strict average. We are going to take the average. We're going to divide by not the number of items, but the number of items minus 1. And we're going to talk about that a little bit, why we do that, why we might do that. So this is going to be I is 1 up to n. And notice in this case, we're not calling our mean mu, we're calling it x bar. But it's really the same formula. The only difference is here. So this will give us an idea of the average squared distance between each data point and the mean. Now, squared distance is going to be a little confusing, and we'll address that in a minute. It's sort of like when you think about a room, the size of a room. If a room is 10 feet by 10 feet, we might say that is 100 square feet. But do we really have a clear concept, unless you're in real estate or you're, doing construction or things like this, do you have a clear concept of what 100 square feet is? Maybe you break it down to being a 10 foot by 10 foot room. That's easier to understand. And I'm just pointing this out because it turns out it's a little tricky to interpret variance when you see it, unless you work with it a lot. And we'll look at a different metric that is built from the variance that kind of corrects for that. Okay, so this n-1, right here, we call this Bessel's correction. And you might be wondering why we do this. Why might we do this? So remember when we were sampling means? Remember when we were sampling means, and sometimes we get a mean way above the mean, above some what the parameter of the distribution would be, or we get a mean far below, or it's fairly close by. Depending on, so we take a sample, and we have x bar. X bar is not the actual mu, is it? So our x bar might be fairly divergent from mu, or it might be really close to mu. We don't know because we have one sample. And I'm not saying that's a problem or anything, but if we average, when we divide by n, if we say divide by n-1, we're widening the result of this average by a little bit. So we're more likely to include the population's true variance in our variance calculation, right? Because if we think about variance, like let's say we have a mean, we have some mean that we've determined, some x bar, and we have some variance that sits around x bar, like so. This is some average squared distance between each data point and the mean, represented by this range. Now, what we want to do, hopefully what we are going to do, is include within this space the more elusive population parameter of the variance. So what we've done effectively, maybe this sits like this. What we've done effectively, right, because x bar could be, our mu could actually be over here or something, right? But we've widened this channel. And so we're more likely to actually include the population variance. So that's the purpose of Bessel's correction. Now, I've been saying this thing that ideally we are going to approach mu with our x bar. Ideally, right? We're hoping we'll do that. The reality of that is different, but that's our hope. We are not necessarily trying to approach our sigma squared. We're not necessarily trying to approach the variance with the population variance with our sample variance. That's not necessarily what we are trying to do or what we can do. And the reason being is that this x bar is going to move around depending on the sample. And we can't necessarily, predict on any given round where that's going to be. And so you would think that if we ran the sample standard deviation over and over again on some random data that we would better approximate sigma squared. And turns out that we don't necessarily. It's fun to play around with that. It's a little bit illuminating. There's a pretty amazing article. I think it's really fascinating on Bessel's correction on Stack Overflow, math.stack exchange. And they talk about, well, what is Bessel's correction really doing and why do we need it? And it's weirder than you might think. But for our purposes, really what we're talking about is we're trying to include the actual variance within our estimate of the variance when we perform Bessel's correction. All right, so we are at a breakout. And notice here, you're going to code a variance function. And we've got two formulas, right? We've got a formula for the population variance and a formula for the sample variance. Notice, hopefully this will let me write on this. Notice we have the summation, right? We've got a summation. This implies a for loop, right? And accumulation. So if we look at all of this, we've got the mean. We've got each data point. And we're going to look at each data point, get the difference between that data point and the mean, square that, sum them all together, and divide by the number of data points, or by the number of data points minus 1, if it's a sample. So what parameters do you need here? Variance, if you're thinking about this in this way, when you call variance, it's going to need two parameters. It's going to need a list that you pass in, and it's also going to need an indicator of whether it's a population or a sample. And we could do something like this. Sample could be the second parameter. Since we're almost always working with samples, you could do sample equals true by default. But feel free to write that however you want. So I'm going to do, let's do 5 minutes on this, and we'll wrap up there for the night after solving it. So go ahead and yeah, go for it. All right, so let's code through this. Okay, all right, that's a big mess. Hopefully that isn't completely unreadable. We'll just go for it. All right. So I'm going to code this pretty quickly, and the reason being I want to just take a minute and show you another metric that we use that is essentially variance, but easier to figure out. So let's say def variance, and we're going to pass in a list, and we're going to assume that this is a sample. So I'm going to set this sample to true. So what do we do from here? Well, we need the mean, right? We need the mean in order to calculate the variance. And I'm just going to make a simple accumulator. I'll call it total. And for each item in the list, so for each number, I could say number, total is going to be incremented by the item minus the mean. Oops. And we're going to square that. You might be thinking maybe there's a version of variance that doesn't use squares and uses absolute values instead. And there is. There's the mean absolute deviation, which is essentially variance, but we don't square. We just take the absolute value of that difference instead and return that. But that's, or the average of that. So that's another version of it. So, this will serve for showing us what we're doing here. So we're going to return the total that we accumulated here, right? That's everything to the right of our summation. And we're going to divide that by the length of the list. If it's a sample, the length of the list minus 1. And otherwise, we're going to return the total divided by the length of the list. So this is another one of those nice places where you can condense a little bit. And I'm going to go ahead and condense this 1 minus sample. And now we can get rid of that line. Okay. So this is a variance function. Let's look at the variance of A. And these are our house prices. And I've got an error here. Let me just fix that. So we'll print the variance of A, and let's assume it's a sample. Okay. Now here's a number. What does this number mean? And remember, this is in thousands. So when we look at this variance, what we're talking about here is 3 more zeros, right? That's a big number. How do we interpret this? I don't think we do, to be honest. I think a lot of the time, our variance is going to be difficult to understand unless we're working with variance all the time. But just like thinking about 100 square feet versus thinking about 10 foot by 10 foot, well, we can just take the square root of this, and that is going to give us something that is a little bit more interpretable. And I'll just do it like this, and then we'll actually wrap that into a function. Okay, 253. If we think about this data, why don't we print the mean while we're at it? Let's print the mean of A. So we have a mean around 620.5, and for the most part, our data sits in this, a lot of our data sits in between 620 plus 253 and 620 minus 253. And so this is interpretable. This looks like an average distance between each data point and the mean. And that's actually what this represents. And so one thing that is funny about this, why don't we print this 2 different ways? We'll print this as if it's a sample, or if it's not a sample. So these are not very different, right? They're not that different. And so there's a bit of an argument between whether or not, if we take this square root of the variance, which is actually the standard deviation, which is more commonly used because it's easier to interpret. This is the standard deviation. There is a bit of an argument about whether or not we should apply Bessel's correction, because it doesn't dramatically change that range, but that's a little bit theoretical. How do we wrap this into a function? How do we write the standard deviation function? It's pretty easy. just saying. We can simply do this. We can say standard deviation of a list. We'll still include Bessel's correction. We can just return the variance. We pass in the list, and we pass in sample, and we take the square root of that. And you can take the square root in a couple different ways, right? We could exponentiate to 1/2, or we could, say from math, import square root, and we could just wrap this in the square root function. Either way is going to be fine. And yeah. And the takeaway from that is standard deviation is a little bit friendlier. And when you're trying to think of the average distance between each data point and the mean, you're probably going to think in terms of standard deviation. So I'll just run that. And we see, the same value, the more inclusive 253, because we're trying to include the population standard deviation, more inclusive than the 240 span of the population calculation. Okay, so that's nice. We actually we're at the end of our measures of spread, so that's perfect. We finished exactly on time. That's lecture for tonight. Feel free to sign off if you've got things to do. If you have questions for me, stay on. I can stay on for about 15 minutes today. And feel free to come off mute and ask any questions you might have.